Near Mars 3I, Atlas did something scientists did not expect. December 3rd, 2025. Was supposed to be routine, or as routine as observing an interstellar visitor passing within 28 million kilometers of another planet could be. Spacecraft had been positioned. Observation sequences had been programmed weeks in advance. International teams had coordinated timing with the precision that defines modern space operations. Everything was ready. Then 3I, Atlas, didn't show up where it was supposed to be, at 14:23 UTC. NASA's Mars Reconnaissance Orbiter executed its programmed slew maneuver, pointing its high-resolution camera toward the predicted coordinates where the interstellar object should appear. The spacecraft's computer, following instructions uploaded days earlier, captured a series of images with exposure times calculated to reveal the faint comet against the star field when those images reached Earth. 13 minutes later, the time required for radio signals to traverse the Earth-Mars distance at the Jet Propulsion Laboratories. Mars Mission Operations Center stared at their screens in confusion. The target coordinates contained nothing but background stars. 31 ATLAS was nowhere to be found. Dr. Richard Zurek, chief scientist for NASA's Mars Program Office, was the first to vocalize what everyone in the control room was thinking. We're looking in the wrong place. Within minutes, the operations team was running emergency calculations, pulling the most recent trajectory data from Earth-based observatories and attempting to determine where 3I actually was relative to Mars. The answer, when it emerged from rapid orbit determination software, was shocking. The object was offset from predictions by more than 400,000 kilometers, roughly the distance from Earth to the Moon. The carefully planned spacecraft observations, timed to capture humanity's closest view of an interstellar visitor, had been pointing at empty space while 3I, Atlas, passed by in an entirely different region of Mars's orbital neighborhood. But the position error was only the beginning of the mystery. When ESA's Mars Express finally located the object, using its wide-field camera more by luck than planning, the images revealed something that would dominate discussion for weeks. 3I appeared to be rotating far more rapidly than earlier observations suggested. Dr. Alejandro Cardacin, Mars Express operations manager, described the observation in a hastily convened video conference with international partners. The brightness variations are occurring on a timescale of minutes rather than hours. Either the nucleus is tumbling chaotically, or we're seeing discrete flares of activity turning on and off as different regions rotate into view. Both scenarios suggest something dramatically changed since the last detailed observations from Earth. The rapid brightness fluctuations created an unsettling, strobe-like effect in time-lapse sequences compiled from the spacecraft images. The comet would brighten by as much as half a magnitude, a 58% increase in light output over periods as short as 8 minutes, then fade again nearly as quickly. The pattern didn't repeat regularly, making it impossible to predict when the next brightening event would occur. This chaotic variability was completely unlike the steady, predictable brightness patterns observed from Earth throughout October and November. Something fundamental had changed in 3I behavior as it approached. Maya's Dr. Colin Snodgrass from the University of Edinburgh, who had been tracking the comet since discovery, was blunt in his assessment. Objects don't just spontaneously develop chaotic rotation or random outbursting without cause. Either 3I, Atlas, experienced some kind of structural event fragmentation, collision with debris, internal disruption, or it's responding to external forces we're not accounting for in our models. The fragmentation hypothesis gained immediate attention. Comet nuclei are notoriously fragile, held together by weak gravity and the structural integrity of ice that can fracture under thermal stress or rotational forces. If 3I Atlas had split into multiple pieces during or after its October perihelion passage, those fragments might now be tumbling independently, each with its own rotation state and activity pattern, but high-resolution imaging from Mars Express, pushed to its absolute limits to resolve detail at the object's actual distance, showed no clear evidence of multiple discrete nuclei. The comet appeared as a single, slightly elongated source surrounded by an asymmetric coma. If fragmentation had occurred, the pieces were either too close together to resolve or too similar in brightness to distinguish. The alternative explanation that external forces were affecting 3-1 ATLA, uncomfortable questions about what those forces might be. Mars's gravitational influence at 28 million kilometers was negligible, far too weak to tidally disrupt the nucleus or significantly perturb its rotation. The planet's thin atmosphere and weak magnetic field couldn't account for the observed changes. Solar radiation pressure and solar wind effects were essentially identical to what the object had been experiencing for months. What external force, operating in the space near Mars, could dramatically alter an interstellar visitor's behavior? Dr. Naling Samarazinga, who had spent decades studying comet rotation dynamics, proposed a different framework for thinking about the observations. Perhaps 3 IATL-AS hasn't changed at all. Perhaps what we're seeing now is its natural state, and the apparently steady behavior we observed from Earth was the anomaly, a temporary phase that ended as the object moved beyond perihelion and entered a different thermal regime. This interpretation suggested that 3 IATLAS's composition, or internal structure, was more complex than standard comet models assumed. If the nucleus contained regions with vastly different volatile contents, thermal properties, or mechanical strength, different parts might respond to solar heating on different timescales. The steady behavior observed earlier might have represented an equilibrium state that couldn't be sustained as the object cooled and receded from the Sun. The rapid light variations correlated intriguingly with spectroscopic observations from Earth-based telescopes that managed to capture spectra during brief windows when the object brightened enough to be detectable. These spectra showed emission lines from sodium and other metals appearing and disappearing on timescales of minutes. That whatever process was driving the brightness changes was also modulating the chemical composition of material being ejected from the nucleus. Dr. Anita Cochrane, analyzing spectra from McDonald Observatory, noted the implications. If metals are appearing and disappearing that quickly, we're seeing either incredibly localized vaporization from small regions that rotate in and out of view, or we're witnessing some kind of impact process where fresh material is being continuously excavated from the interior. The impact scenario was speculative but not impossible. The inner solar system contains enormous quantities of microscopic dust debris from asteroid collisions, comet disintegration, and billions of years of planetary evolution. Objects traveling at high relative velocities through this dust environment experience continuous low-level bombardment. For a typical comet nucleus with rotation period measured in hours, these impacts would average out into steady background noise. But if 3I, Atlas, was rotating extremely rapidly or tumbling chaotically, impacts might create discrete flashes as high-velocity dust grains struck fresh ice and vaporized it, explosively calculating the required dust density and impact rates too. Produce the observed effects yielded numbers that were marginally plausible but stretched credulity. The bombardment scenario required dust densities at least 10 times higher than typical. Values for Mars's orbital region in localized streams or clouds, but difficult to reconcile with the general environment as December progressed and Mars orbiters continued their opportunistic observations whenever 3IATLAS passed through their fields of view. A troubling pattern emerged. The object's trajectory continued deviating from gravitational predictions, but now the deviations themselves were becoming unpredictable. Instead of steady acceleration in a consistent direction, 3.1 ATLA appeared to be jinking, making small, irregular course corrections that defied simple modeling. Dr. Stephen Chesley at JPL, attempting to fit orbital models to the accumulating position measurements, described the challenge. It's like trying to predict the path of a balloon losing air through multiple random holes. Each observation gives us a snapshot of where the object is, but projecting forward becomes increasingly uncertain because we don't know which way or how hard the next thrust will push it. The trajectory uncertainty had immediate practical consequences. Earth-based observatories trying to track 3I Atlas found their predicted positions increasingly unreliable. The object that should appear at specific coordinates based on gravitational calculations would actually be offset by thousands or tens of thousands of kilometers small angles in the sky, but large enough to place it outside narrow telescope fields of view. Scientists were terrified, though they'd never used that word in official communications. The proper scientific term was concerned or puzzled, but in private conversations, in emails between colleagues, in late-night video calls discussing the latest observations, the emotion was closer to fear not of physical danger, but of confronting a phenomenon that systematically violated expectations and resisted every attempt at explanation. The brightness fluctuations weren't random. That realization came on December 8, when Dr. Matthew Knight's team at the U.S. Naval Academy completed a comprehensive analysis of all available photometric data from the Mars encounter period. There's structure in the chaos, Knight explained during a presentation to the Small Bodies Assessment Group. His screen showed a power spectrum analysis, a mathematical technique that reveals hidden periodicities in apparently random data. We're seeing 3 distinct timescales of variation: an 8-minute component, a 47-minute component, and underlying modulation at approximately 5.2 hours. The 5.2-hour period matched earlier rotation estimates for the nucleus itself, suggesting the comet was indeed spinning, but faster than previously calculated. The 47-minute period was more puzzling, possibly representing a large surface feature or secondary rotation mode. But the 8-minute variations were completely unprecedented in comet observations. Nothing on a solid nucleus can physically change that fast, Knight continued. Rock doesn't reconfigure itself every 8 minutes. Ice sublimates on thermal timescales, measured in hours or days, not minutes. Whatever is causing these rapid brightness changes isn't tied to the rotation of a solid body. Dr. Jessica Sunshine from the University of Maryland proposed a radical interpretation. What if we're not seeing rotation at all? What if we're seeing discrete ejection, events, jets of material erupting from the surface, brightening the overall coma, then fading as the material disperses? That could produce brightness variations on any timescale, limited only by how quickly subsurface pressure can build and release. The jets hypothesis had appealed because it explained both the rapid variations and the spectroscopic metal detections. If high-pressure gas was breaching through the surface in violent outbursts, it could entrain metal-rich dust particles and vaporize them through friction and shock heating. Each eruption would create a temporary brightening as hot material caught sunlight, followed by fading as the ejector cooled and dispersed. But testing this model required understanding what could drive such violent, frequent eruptions. On Earth, geysers erupt when underground water is heated to steam, building pressure until it exceeds the overburdened strength and blasts through to the surface. Old Faithful in Yellowstone National Park erupts roughly every 90 minutes through this mechanism. Could something similar operate in a comet nucleus 2.3 astronomical units from the Sun? Dr. Michael Ahern, who had led the Deep Impact mission that deliberately crashed a projectile into Comet Tempel 1, knew comet subsurface structure better than almost anyone. His assessment was cautiously supportive. We know from Deep Impact that comet nuclei have layered structure with distinct horizons of different materials. It's plausible that 3I Atlas has volatile-rich pockets reservoirs of highly pressurized CO2 or CO trapped beneath less volatile layers. As the overlying material sublimates away or fractures from thermal stress, these pockets could suddenly decompress, creating the violent eruptions we're inferring. This model predicted something testable. If eruptions were blowing through progressively thinning overlying layers, they should become more frequent over time as the covering material was removed. Examining the time series of brightness variations revealed exactly this trend. In early December, the 8-minute brightening events occurred sporadically, separated by hours of relative quiescence. By mid-December, they were happening continuously, creating an almost stroboscopic effect in time-lapse. Observations, the accelerating eruption rate suggested 3I Atlas was undergoing fundamental structural change, transitioning from a relatively stable configuration to an increasingly active, possibly unstable state. What would happen when the confining layers were completely removed and the subsurface volatile reservoirs were fully exposed to solar heating? Dr. Nalin Samarasina ran thermophysical models exploring this scenario. His results were sobering. If a significant fraction of the nucleus volume consists of supervolatile ethers that suddenly become exposed, the resulting outgassing could exceed the nucleus's self-gravity. At that point, you don't have a comet anymore. You have an expanding debris cloud. The fragmentation scenario had resurfaced, but now with a specific physical mechanism and timeline. If Samarasina's models were accurate, 3.1 Atlas might disintegrate entirely within weeks as progressive erosion exposed its volatile-rich interior. Meanwhile, Mars orbiters continued their opportunistic observations, capturing data whenever the unpredictable object happened to cross their fields of view. The UAE's HOPE probe, equipped with an ultraviolet spectrometer designed to study Mars's upper atmosphere, detected something unexpected when 3I Atlas passed through its observation region on December 11th. The ultraviolet spectrum showed strong emission lines from atomic oxygen, stronger than could be explained by photodissociation of water vapor. Atomic oxygen requires either very high temperatures, several thousand Kelvin, or energetic particle impacts to produce in significant quantities. Neither mechanism seemed applicable to a comet more than 300 million kilometers from the Sun. Dr. Hessel Matrucci, Hope's science lead, was frank in her assessment. This doesn't make sense with conventional comet chemistry. We're seeing oxygen emission that would be appropriate for a much hotter environments, something closer to the Sun's corona than a comet at Mars's distance. Either our understanding of UV-driven photochemistry is seriously incomplete, or there's an energy source we're not accounting for. The energy puzzle kept returning in different forms. The rapid eruptions required energy. The high-temperature molecules required energy. The atomic oxygen required energy. The anomalous trajectory deviations required energy. Every observation seemed to demand power inputs that solar heating alone couldn't provide. Dr. David Jewett at UCLA attempted to quantify the total energy budget. His calculations showed that sustaining the observed activity levels, the eruptions, the metal vaporization, the oxygen excitation, required approximately Y a watts continuously. For comparison, that's roughly the electrical generating capacity of a small country, all focused on an icy nucleus, perhaps 5 kilometers in diameter. Solar illumination at 2.3 astronomical units provided about YP, watts, striking the nucleus's cross-section enough in principle, but only if energy conversion efficiency approached 10%. Natural processes like ice sublimation typically achieve efficiencies below 1%, getting 10 times higher. Efficiency required something fundamentally different from standard. Comet physics. Chemical energy from exothermic reactions offered a potential explanation. If 3IATLAS's interior contained compounds that could react energetically when mixed, perhaps reduced and oxidized species that had been kept separate during the object's formation but were now being brought into contact by erosion and fracturing the resulting reactions, could release substantial heat. Dr. Kerry Lees from Johns Hopkins Applied Physics Laboratory, who specialized in cometry chemistry, explored this possibility. Some interstellar models predict that objects forming in certain environments might incorporate unusual chemistry, metallic iron alongside water ice. For example, if such materials are mixing for the first time as the nucleus erodes, redox reactions could release energy orders of magnitude beyond what sublimation alone provides. The chemical energy hypothesis was tantalizing but difficult to test. It predicted specific compositional sicknesses, elevated iron and oxygen in particular ratios that would be visible in higher resolution spectra. But obtaining such spectra required the comet to be bright enough and positioned favorably enough for extended observations with large telescopes. As 3I Atlas continued fading and moving around, such observations became increasingly difficult. On December 15th, the Keck Observatory in Hawaii obtained what would become one of the highest quality spectra during the Mars encounter period. The 4-hour exposure, obtained during rare conditions of exceptional atmospheric stability, revealed emission lines from no fewer than 23 distinct molecular and atomic species, more diversity than typically seen in solar system comets. Dr. Bonnie Burati, analyzing the Keck spectrum, was struck by the complexity. This reads like a periodic table rather than a comet. We're seeing emission from sodium, potassium, calcium, iron, nickel, manganese, essentially every abundant metal plus carbon-bearing molecules, nitrogen compounds, and oxygen species in multiple ionization states. The chemistry is extraordinarily rich and That diversity supported the hypothesis that 3IATLAS was compositionally heterogeneous, not a uniform mixture, but rather a conglomeration of materials with different origins and formation histories. Perhaps it had accreted from multiple parent bodies or formed in a region of its birth. Protoplanetary disk, where materials from different temperatures and pressures were mixed together. As December progressed toward the year's end, the observations from Mars orbiters diminished as 3I Atlas moved beyond their effective range. The object was now receding from both Mars and Earth, growing fainter and more difficult to observe with each passing day. The brief window of close-range spacecraft observations had closed, leaving behind data that raised more questions than it answered. The light variations continued, visible in Earth-based telescope observations as an incessant flickering that made the comet look almost alive, cosmic lighthouse signaling in irregular patterns that seemed to carry meaning without being decipherable. What was 3I Atlas trying to tell us? Or, more precisely, what was the universe revealing about the diversity of objects traveling between stars? The correlation was subtle enough that it took nearly 2 weeks to notice. Dr. Gina de, project scientist for NASA's MAVEN mission, studying Mars's atmosphere and magnetic environment, was reviewing spacecraft data when she spotted something odd in the timing of 3IATLAS's brightness. Variations. The flares aren't entirely random, she told colleagues during a December 19th analysis meeting. There's a weak but statistically significant correlation with MAVEN's measurements of Mars's induced magnetotail, the magnetic field structure created by solar wind, interaction with the planet's thin atmosphere. Mars lacks Earth's strong global magnetic field, but it does have localized magnetic fields in its crust and a complex magnetosphere created by solar wind interactions. This induced magnetotail extends millions of kilometers downstream from the planet, creating regions where magnetic field strength and orientation vary dramatically over relatively short distances. Analysis showed that 3IATLAS's brightness flares were slightly more frequent when the comet was positioned in regions where MAVEN measured enhanced magnetic field turbulence. The correlation was weak, explaining perhaps 15% of the variance in flare timing, but it was real and reproducible in independent datasets. If this correlation is physical rather than coincidental, Di Braccio continued, it suggests 3IATLAS is somehow responding to the magnetic environment it's moving through. That's unprecedented for a comet. Comets interact with solar, wind, magnetic fields all the time, but they don't typically show brightness variations tied to local magnetic conditions. The magnetic coupling hypothesis opened new theoretical territory. Comets develop their own magnetic fields through a process called mass loading. The solar wind picks up ions from the coma, creating currents that generate magnetic fields. These induced magnetospheres can interact with external magnetic fields through reconnection events and other plasma physics processes, but the effects are typically gradual and smooth, not the sudden brightness flares observed in 3IATLAS. Something about this object's interaction with magnetic fields appeared fundamentally different from standard comet behavior. Dr. Thomas Gambosi from the University of Michigan, an expert in comet plasma physics, proposed a mechanism. If 3I Atlas has regions of exposed metallic material on its surface, perhaps grains from its formation environments, could become electrically charged through photoelectric effect and interaction with the solar wind. When the comet moves through regions of varying magnetic field, the charged grains experience Lorentz forces that could literally pull them off the surface, creating sudden ejection events. This electrostatic ejection mechanism was speculative but physically plausible. It predicted that the ejected material should be enriched in metals relative to ices, matching the spectroscopic observations of sodium and iron emissions. It also predicted that ejection should be most violent in regions of rapid magnetic field change consistent with the correlation between flares and magnetale turbulence. Testing the hypothesis required understanding the electrical properties of 3I-ATLAS's surface, which in turn depended on composition and structure that remained poorly constrained. But if the mechanism was operating, it represented a completely new mode of comet activity driven by electromagnetic forces rather than thermal sublimation. Meanwhile, ESA's Mars Express was documenting another puzzling aspect of the Mars. Encounter 3, I Atlas, appeared to be leaving a trail. High-sensitivity imaging revealed a faint streamer of material extending behind the comet's position, aligned roughly with its trajectory. This wasn't the normal dust tail pushed by solar radiation. It was too narrow and too closely aligned with the velocity vector. Dr. Gerhard Schwemm, former ESA mission manager for Rosetta, analyzed the trail morphology. This looks more like a debris stream than a pressure-driven tail. It's as if the nucleus is shedding material continuously, leaving a breadcrumb trail marking where it's been. The particles aren't being pushed by radiation or gas drag. They're maintaining nearly the same orbital velocity as the parent body. Debris streams typically form when fragile bodies break apart, with fragments following similar orbits that slowly diverge over time. But detailed imaging showed no evidence of discrete fragments large enough to produce their own comet. Whatever was creating the trail consisted of small particles or gas moving at velocities barely different from the nucleus itself. One possibility was that the rapid eruptions were ejecting material at very low velocities, just meters per second rather than the hundreds of meters per second typical of comet jets. Material ejected this slowly would remain gravitationally bound to the nucleus unless the eruption velocity exceeded the escape velocity of about 2 to 3 meters per second. For an object of 3 IATLAS's estimated size, Dr. Naylan Samaresina calculated the mass loss rate required to produce the observed trail. If the trail has been forming continuously since the Mars encounter began, we're looking at roughly 100 kilograms per second being shed from the nucleus. Over the 2 weeks Mars spacecraft have been observing, that's about 120,000 tons of material comparable to the mass of a decent building. For a nucleus estimated at 5 kilometers diameter with typical comet density around 500 kilograms per cubic meter, losing 120,000 tons represented approximately 0.2% of the total mass. Not catastrophic, but significant and if the loss rate was accelerating as the eruption frequency increased. The cumulative effect over months could become substantial. The trail's existence also provided a natural explanation for one of the trajectory anomalies. Material ejected backward along the velocity vector would create thrust, pushing the object forward, exactly the type of acceleration that could explain some of the observed deviations from gravitational predictions. If eruptions were preferentially ejecting material in specific directions tied to nucleus orientation, The integrated effect over time could produce significant trajectory changes, but this mechanism required the eruptions to be highly directional and persistent over long periods, characteristics that seemed inconsistent with the apparently chaotic nature of the activity, unless the chaos was only apparent, masking some underlying order that wasn't yet visible in the data. On December 21st, a team led by Dr. Bin Yang at ESA's Very Large Telescope obtained time-resolved spectroscopy that revealed something extraordinary. The emission lines from different chemical species weren't fluctuating in phase. Sodium emissions would peak, then fade, then calcium emissions would peak, then ionas if different regions of the nucleus were activating in sequence. It looks almost choreographed, Yang observed during data analysis, like there's a wave of activation propagating around the surface, triggering different compositional zones at different times. I've never seen anything like this in a comet. The sequential activation pattern suggested some kind of coupling between different regions of the nucleus, perhaps thermal conductivity carrying heat from active areas to adjacent dormant regions, triggering their activation in cascade fashion, or perhaps pressure waves propagating through the porous interior, triggering eruptions as the pressure pulse reached pockets of trapped volatiles. Dr. Jessica Agarwal proposed yet another interpretation. What if the nucleus has a layered structure like an onion, with different compositional shells at different depths? As the surface erodes, it exposes successive layers enriched in different elements. The sequential activation we're seeing might just be excavation proceeding through these layers, with each new surface composition dominating the spectrum temporarily before being eroded away. All three mechanisms, thermal coupling, pressure waves, and layered excavation, could potentially explain the observations. Distinguishing between them required information about nucleus internal structure that simply wasn't available from remote observations. It would have required a spacecraft at close range, imaging the nucleus directly and monitoring surface changes in real time. The missed opportunity represented by the trajectory prediction failure weighed heavily on the science teams. If Mars orbiters had successfully observed 3I Atlas at the planned 28 million kilometer distance, they might have resolved nucleus features, detected compositional variations across the surface, and directly observed the eruption mechanism. Instead, the observations from actual distances of tens of millions of kilometers provided only indirect evidence and frustratingly ambiguous clues. As the Mars encounter period drew to a close and 3I Atlas continued receding from both Mars and Earth, the scientific community was left with a complex and contradictory picture. The object showed rapid brightness fluctuations on 8-minute timescales, correlation with Mars's magnetic environment, sequential activation of different chemical species, a debris trail aligned with its trajectory, continuing unpredictable trajectory deviations, accelerating eruption frequency suggesting structural evolution. Each observation was solid and reproducible. The challenge was synthesizing them into a coherent physical model that explained everything simultaneously without requiring implausible coincidences or ad hoc assumptions. Dr. Michael Ahern, reflecting on 4 decades of comet research, offered perspective. Every comet we've studied up close has surprised us. We thought we understood comets until we sent spacecraft to them and discovered they were far stranger than our Earth-based observations suggested. 3.1 ATLAS is reminding us that lesson applies doubly to interstellar. Visitors' objects formed in environments we've never sampled, carrying chemistry we've never analyzed, behaving in ways our models never anticipated. The Mars encounter hadn't answered the fundamental questions about what 3180LAs was and why it behaved so strangely. But it had transformed those questions from abstract puzzles into urgent priorities with clear observational signatures and potential mechanisms to test. Dr. Anita Cochrane had been analyzing cometary spectra for 30 years. She knew what comet emission lines should look like, the characteristic patterns of hydroxyl from water dissociation, cyanogen's distinctive blue bands, the subtle signatures of carbon monoxide and methane. On December 23rd, staring at her computer screen at McDonald Observatory, she was looking at something that violated every pattern she'd internalized over 3 decades of observation. "This spectrum is impossible," she muttered to her graduate student, who had just arrived with coffee. "Or rather, it's possible, but it requires conditions that shouldn't exist in a comet at this distance from the Sun." The spectrum, obtained during a rare moment when 3I-ATLAS brightened enough to capture sufficient signal, showed emission lines from triply ionized carbon C4. Creating this ion requires stripping 3 electrons from carbon atoms, which demands either temperatures exceeding 100,000 Kelvin or bombardment by highly energetic particles. C4 appears in the Sun's corona, in stellar atmospheres, in the hot gas surrounding active galactic nuclei, Cochrane explained. It doesn't appear in comets at 2.3 astronomical units from the Sun. The energy environment is completely wrong. But there it was, unmistakable in the ultraviolet spectrum, the characteristic doublet at 1548 and 1550 angstroms, exactly where C4 should appear. The signal-to-noise ratio was marginal but sufficient to rule out instrumental artifact or misidentification. 31ATL AS was somehow producing highly ionized carbon in quantities detectable from Earth. The discovery triggered immediate follow-up observations. The Hubble Space Telescope, which had successfully observed the comet during its bright phase in October, was redirected toward 3I-ATLAS's current position for ultraviolet spectroscopy. HST's superior sensitivity and resolution would either confirm the C for detection or reveal it as some subtle misinterpretation of ground-based data. On December 27th, the HST spectrum arrived. It not only confirmed C4, but revealed something even more remarkable: emission from OV oxygen stripped of 5 electrons, requiring even more extreme conditions. The oxygen ion appeared weaker than carbon, but was unambiguously present. Dr. John Raymond from the Harvard-Smithsonian Center for Astrophysics, whose career had focused on highly ionized plasmas in astrophysical contexts, was brought in to interpret the observations. His assessment was delivered with the careful precision of someone aware they were describing something genuinely unprecedented. These ionization states require either temperatures around 300,000 Kelvin or particle energies in the kiloelectron volt range. We're looking at conditions more typical of a collisional shock or magnetic reconnection event than anything associated with comet activity. If this emission is coming from the comet's immediate environment and the positional coincidence suggests it is, we need to identify an energy source far more powerful than solar ultraviolet radiation. 3 mechanisms could potentially produce such extreme ionization. First, the comet might be moving through an unusually dense region of the solar wind, creating a bow shock where inflowing plasma was compressed and heated to extreme temperatures. Second, Magnetic reconnection events in the comet's induced magnetosphere might be accelerating particles to high energies, which could then collisionally ionize ambient gas. Third, and this was the explanation, nobody wanted to seriously propose some internal energy source within the nucleus might be driving energetic processes in the surrounding coma. That Bohr hypothesis seemed most plausible initially. Spacecraft monitoring solar wind conditions showed that late December featured elevated solar wind density and velocity. A high-speed stream from a coronal hole was sweeping past Earth's orbit. If 3I Atlas was encountering this same enhanced solar wind, the resulting bow shock might be energetic, enough to produce highly ionized species. But calculations by Dr. Thomas Gambosi's group at Michigan revealed a problem. Even with enhanced solar wind, the predicted shock temperature peaked around 50,000 Kelvin to cool by a factor of 6 to efficiently produce. Getting temperatures high enough required solar wind velocities exceeding 1,000 kilometers per second, nearly twice what spacecraft were measuring. Unless, Gambosi noted, the comet's own motion through the solar wind is contributing substantial relative velocity. 3.1 ATLAS is moving at 22 kilometers per second relative to the Sun, which adds to the solar wind velocity in its reference frame. But even accounting for this, we fall short of required shock speeds. The magnetic reconnection hypothesis was harder to evaluate, because it depended on magnetic field geometry that couldn't be directly measured without InSight spacecraft. Reconnection events could theoretically accelerate particles too arbitrarily, high energies depending on magnetic field strength and topology. The weak correlation between brightness variations and Mars's magnetail suggested magnetic fields were, indeed, relevant to 3I Atlas's behavior. Supporting this mechanism, at least in principle, Dr. Mihai Desai from the Southwest Research Institute, an expert on particle acceleration in space plasmas, outlined the requirements to produce the observed highly ionized species through particle acceleration. You need magnetic fields of roughly 100 nanotesla undergoing rapid reconnection. That's about 10 times stronger than typical induced magnetospheres around comets. It's possible if the comet has unusual magnetic properties, perhaps carrying remnant magnetization from its formation, environment, or generating enhanced fields through unexpectedly strong ionospheric currents. The internal energy source hypothesis was deliberately left vague because nobody wanted to specify what such a source might be. Chemical reactions, even the most energetic redox processes, couldn't produce temperatures of hundreds of thousands of degrees. Radioactive decay of short-lived isotopes could provide sustained power but required recent nucleosynthesis, possible only if the object had been near a supernova or similar extreme environment within the past few million years. On December 30th, Dr. Avi Loeb published a brief technical note exploring an alternative that the mainstream community had been studiously avoiding. If natural mechanisms prove insufficient to explain observed ionization states, we should consider whether electromagnetic or plasma processes of technological origin might be involved. This is not a claim of artificial activity, but rather an acknowledgement that our hypothesis, space, should include all physically possible mechanisms, even uncomfortable ones. The response was immediate and polarized. Some researchers appreciated Loeb's willingness to explicitly state what many were privately considering. Others criticized the suggestion as premature speculation that risked undermining serious scientific analysis with sensationalism. Dr. Michelle Bannister articulated the mainstream position. Extreme observations require thorough investigation of extreme, natural mechanisms before invoking non-natural explanations. Interstellar objects formed under conditions we've never directly sampled. Their chemistry, structure, and behavior may include phenomena that seem impossible based on solar system experience, but are actually natural consequences of formation environments unlike our own. The debate highlighted a fundamental challenge: distinguishing between impossible by natural means and improbable but natural required comprehensive understanding of what natural processes could produce under exotic conditions. That understanding remained incomplete, leaving ambiguous whether highly ionized emissions represented a puzzle, requiring new natural physics or evidence of something fundamentally different. Meanwhile, independent confirmation of the ionization anomaly came from an unexpected source. Amateur astronomer Tony Hallis, known for exceptionally deep astrophotography, had obtained narrowband images of 3I Atlas using filters designed to isolate specific emission lines. His images, processed to reveal faint structures, showed something peculiar: a faint blue halo surrounding the main coma, visible only in ultraviolet sensitive imaging. Professional analysis of Hallis's images revealed the blue emission was strongest in directions perpendicular to the Sun, suggesting it originated from material exposed to solar wind from the side rather than directly upstream. This geometry was consistent with bow shock emission, supporting natural explanations based on plasma physics rather than internal energy sources. Dr. Carl Schmidt from Boston University, who specialized in UV imaging of planetary atmospheres, examined the morphology, the spatial distribution of highly ionized emission matches what we'd expect from a collisional shock heated by comet-solar wind interaction. It's unusual in intensity, much brighter than typical comets, but not qualitatively different in structure. This suggests we're seeing an extreme example of a natural process rather than something categorically new. As December ended and 3I Atlas faded past magnitude 13, the spectroscopic observations became progressively more difficult. The highly ionized emission lines were faint even when the comet was relatively bright. At its current luminosity, only the largest telescopes could detect them, and then only during rare favorable conditions. The final confirmed detection of C4 came from the Keck Observatory on January 4, 2026. After that, the comet faded below the threshold where ultraviolet spectroscopy could reliably detect trace species. The ionization mystery would remain unresolved, leaving behind data that documented extreme conditions, but couldn't definitively identify their cause. What was clear was that 3.1 Atlas continued defying simple categorization, accumulating anomalies faster than explanations could be developed. Each new observation added complexity rather than clarity. The question seemed almost absurd initially. Mars, a planet with a mass 6.4 times 10 kilograms, influenced by a comet nucleus perhaps 5 kilometers across, weighing maybe 10 kilograms, a trillion times less massive. The gravitational interaction should be utterly negligible. A cosmic rounding error. Yet, on January 7, 2026, Dr. James Green, former NASA chief scientist and planetary atmospheres expert, raised a possibility that made mission planners at the Mars Exploration Program sit up and take notice. 3 AS passed within approximately 28 million kilometers of Mars, though not where predicted. That's close enough, that if the comet was outgassing asymmetrically at the rates we're inferring from activity observations, it could have deposited measurable quantities of material into Mars's orbital path. Not enough to affect the planet directly, but potentially enough to create a temporary debris stream that Mars will encounter during future orbits. The concept was straightforward. Comets continuously shed material dust, particles, gas molecules, and occasional larger fragments, which spreads out along their orbital paths. Earth encounters these debris streams regularly, producing meteor showers when our planet plows through the dust trails left by periodic comets. The Perseids in August come from Comet Swift-Tuttle. The Leonids in November from Comet Tempel-Tuttle. Could 3I Atlas have left similar debris that Mars might encounter? Dr. Apostolos Christou from the Arma Observatory calculated the geometry. The relative velocity between 3I Atlas and Mars was approximately 18 kilometers per second at closest approach. Material ejected from the comet at typical speeds of a few hundred meters per second would be nudged into slightly different orbits. Some of this material could end up on trajectories that intersect Mars's orbit, potentially creating meteor activity if Mars passes through the debris stream at the right time. The timing was uncertain because it depended on precisely where along Mars's orbit the debris stream would concentrate, which in turn depended on the ejection velocity, distribution, and timing of the comet's out. But crude estimates suggested Mars might encounter concentrated debris anywhere from a few weeks to several months after the comet's passage. More intriguingly, 31ATLAS's debris wouldn't be ordinary solar system material. It would be carrying chemical signatures and potentially isotopic ratios from another stellar system, dust deposited directly into Mars's environment. If any of this material survived atmospheric entry and reached the surface, it would represent physically accessible samples of extrasolar material. Dr. Tomoko Arai from Japan's Institute of Space and Astronautical Science outlined the scientific value. We've collected interstellar dust particles in Earth's stratosphere using high-altitude aircraft, but these samples are tiny micrometers in size and their interstellar origin must be inferred from isotopic anomalies. If 3IATLAS debris reaches Mars's surface and can be identified, it could provide much larger samples with unambiguous extrasolar provenance. The practical challenge was identification. Mars's surface is already covered with billions of years of accumulated dust from asteroid and comet impacts, atmospheric deposition, and volcanic activity. Finding fresh material from a specific source would require either witnessing meteor activity in real time or identifying distinctive chemical or isotopic signatures that unambiguously pointed to 31ATLAS origin. NASA's Perseverance rover, currently exploring Jezero crater, carried instruments that could potentially detect unusual atmospheric phenomena or fresh deposits. The Mars Environmental Dynamics Analyzer MEDA monitored atmospheric conditions, including dust loading. If 3IATLAS debris created meteor activity, MEDA might detect transient atmospheric disturbances or elevated dust levels. More speculatively, if large enough particles survived to impact near the rover's location, the SuperCam instrument could analyze their composition using laser-induced breakdown spectroscopy, detecting the unusual metal-enriched chemistry observed in 3IATLAS's spectroscopic observations. Would be strong evidence of origin from the interstellar visitor, but the probability of debris landing specifically near Perseverance's location was astronomically small. Mars's surface area spans 145 million square kilometers. The rover explored a region measured in square kilometers. Unless the debris stream was extraordinarily concentrated, the odds of material landing within observation range were negligible. ESA's trace gas orbiter offered better prospects. From its orbit several hundred kilometers above Mars, TIGO's instruments could potentially detect meteor activity across the entire daylight hemisphere. The NADA, an occultation for Mars Discovery Nomad spectrometer, designed to measure atmospheric composition, might detect transient enhancements in sodium, iron, or other metals if meteors are blotted in the upper atmosphere. Dr. Anne Corinne Vandel, Nomad Principal Investigator, was cautiously optimistic. We've observed meteor-related metal layers in Earth's atmosphere are transient, enhancements of sodium and iron deposited by ablating meteoroids. If 3IATLAS creates similar activity at Mars, and if the composition is as metal-rich as spectroscopy suggests, Nomad should be sensitive enough to detect it. The observation strategy involved monitoring for several weeks starting in mid-January, watching for sudden enhancements in atmospheric metal content that couldn't be explained by normal meteor activity or dust storm processes. Any detected enhancements would need to be correlated with the predicted geometry of potential debris streams to establish plausible connection to 3.1 Atlas. Beyond the direct effects of debris deposition, researchers began questioning whether 3IATLAS's magnetic interactions inferred from the correlation with Mars's magnetic might have affected the planet's space environment. Mars's thin atmosphere is slowly eroding into space, stripped away by solar wind interactions over billions of years. Could the comet's passage have triggered enhanced atmospheric loss? Dr. Shannon Curry, MAVEN Principal Investigator, examined spacecraft data from the encounter period. We're seeing some interesting variability in ionospheric structure and escape rate measurements, but it's difficult to attribute causation. Mars's upper atmosphere responds to solar wind conditions, which, very naturally, separating comet-related effects from normal solar wind variability requires careful analysis. MAVEN's measurements showed ionospheric density fluctuations during early December consistent with enhanced turbulence or wave activity. The escape rate of oxygen ions, a key indicator of atmospheric loss, increased by approximately 30% during December 3rd to 7th. Then returned to normal levels. The timing overlapped with 3IATLAS's closest approach, but it also overlapped with elevated solar wind pressure from the high-speed stream mentioned earlier. Correlation isn't causation, Curry emphasized. We need to be very careful about claiming the comet affected Mars when solar wind conditions were independently variable. That said, the ionospheric disturbances are interesting and worth investigating further. One mechanism that could plausibly connect 3IATLAS to Martian atmospheric effects involved magnetic field perturbations. If the comet's induced magnetosphere was unusually strong as suggested by the highly ionized emission observations, might have temporarily altered the magnetic field geometry around Mars, changing how solar wind interacted with the ionosphere. Dr. David Brain from the University of Colorado Boulder, who specialized in Mars's magnetic environment, was skeptical but intrigued. Mars's crustal magnetic fields create a complex patchwork of magnetic structures in the upper atmosphere. Adding an external perturbation from a passing magnetized body could, in principle, reorganize these structures temporarily. Whether a comet at 28 million kilometers could produce strong enough fields to matter is questionable, but not impossible if 3IATLAS's magnetic properties are as unusual as other observations suggest. The debate highlighted how little was known about the magnetic properties of interstellar objects. No spacecraft had ever measured magnetic fields near an interstellar visitor. The assumption that comets carried negligible magnetic signatures came from solar system experience. But 3I Atlas was systematically violating assumptions based on solar system objects. As January progressed and spacecraft continued monitoring Mars's environment for potential comet-related effects, public interest in the Mars connection grew. Social media filled with speculation about what interstellar material might do if it reached the Martian surface. Science fiction scenarios about exotic chemistry or biological materials from other stellar systems captured imaginations, even though scientists emphasized the reality would be far more mundane as particles with interesting isotopic ratios, not alien artifacts. Dr. Pamela Gay addressed the speculation directly in a YouTube video. Let's be clear about what we're discussing. If any material from 3IATLAS reaches Mars, and that's still an if, it would be microscopic dust particles, not biological material or technology. These particles would tell us about the chemical composition of material in another stellar system, which is scientifically valuable, but they're not going to be mysterious or dangerous. Yet even mundane dust particles carried profound implications. They would represent physically accessible samples of matter from light years away, formed in a stellar environment with potentially different elemental abundances, temperature histories, and chemical processes than our solar system experienced. Each particle would be a messenger from another world, carrying information encoded in its atomic structure about conditions we could never directly observe. The possibility, however remote, that humanity might already possess samples of extrasolar material sitting in Mars' atmosphere or on its surface, waiting to be identified and studied, transformed how researchers thought about the mission priorities for Mars exploration. By mid-January 2026, orbital dynamicists had accumulated enough position measurements to attempt comprehensive trajectory reconstruction. What emerged from the analysis was more confusing than any single anomalous observation. It was a pattern of motion that seemed to violate basic conservation laws. Dr. Davide Farnocchia at JPL's Center for Near Object Studies led the analysis team. On January 18th, he presented findings to an invited group of dynamicists and planetary scientists that left the room in stunned silence. The integrated acceleration over the Mars encounter period doesn't match the velocity change we observe, Farnocchia began, his presentation displaying vectors and orbital elements that should have aligned but didn't. According to our best fit non-gravitational acceleration model, 3.1 Atlas should have gained approximately 2.3 meters per second in velocity. The actual velocity change, derived from positional measurements before and after the encounter, is 3.7 meters per second. We're missing 1.4 meters per second, about 60% additional velocity change that isn't accounted for by the acceleration we measured. The discrepancy was massive by the standards of precision orbit determination. It meant either the position measurements were systematically wrong, the acceleration measurements were incomplete, or something had imparted momentum to 3I Atlas through a mechanism that wasn't being detected. Dr. Steve Chesley, who had been working parallel analysis, confirmed the finding. I initially thought this was a modeling artifact, some subtle interaction between different force components that was being double counted or missed. But I've tried every possible dynamical model configuration, and the discrepancy persists. The object gained more velocity than the observed forces can explain. 3 explanations seemed possible. First, the comet experienced an impulsive, sudden velocity change, occurring essentially instantaneously, like a collision or explosive outgassing burst that happened between observation windows and wasn't directly measured. Second, the acceleration wasn't constant but varied rapidly in ways that were averaged out in the episodic observations, causing the integrated effect to differ from simple models. Third, there was an additional force operating that observations hadn't detected. The impulsive event hypothesis had some support. The chaotic brightness variations and evidence for violent eruptions suggested the nucleus was structurally active. A sufficiently large eruption could potentially eject enough material fast enough to produce measurable recoil, essentially turning the comet into a natural rocket engine firing a brief but powerful thrust. Dr. Nayland Samarasinha calculated the required eruption magnitude to produce 1.4 meters per second velocity change through recoil requires ejecting roughly 0.5% of the nucleus mass at speeds around 300 meters per second. Assuming a nucleus mass around 1013 kilograms, that's an enormous eruption, equivalent to exploding a small mountain in a matter of minutes or hours. If such an event occurred, we should have seen a dramatic brightness spike. Reviewing the photometric observations revealed several candidates' brightness increases of a full magnitude or more occurring over periods of hours. Any of these could potentially represent the required explosive output, but converting brightness increases to mass ejection rates required assumptions about dust-to-gas ratios, particle size distributions, and ejection velocities that were poorly constrained. The variable acceleration hypothesis was harder to test because it required essentially continuous monitoring to catch rapid changes. The observations, while extensive, were episodic snapshots separated by hours or days. If acceleration varied on shorter timescales, the true time-averaged effect could differ substantially from what interpolation between observations suggested. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics specialized in orbit determination for objects with non-gravitational forces. His assessment was sobering. We're fundamentally limited by temporal sampling. When an object's acceleration changes faster than our observation cadence, we can't fully reconstruct its motion. We see the endpoints where it was before and after, but the path between becomes increasingly uncertain. 3.1 ATLA may be varying its acceleration on timescales of minutes to hours, which would be nearly impossible to capture with current observation strategies. The undetected force hypothesis was the most troubling because it raised questions about what might be missed by current observation techniques. All the acceleration measurements came from astrometry tracking position changes over time. If a force operated without producing detectable optical signatures, it could systematically evade observation while still affecting motion. What forces fit this description? Electromagnetic effects, if present, might not produce visible light. Gravitational interactions with small, dark objects wouldn't be directly visible. Even some forms of outgassing, particularly if dominated by transparent gases like nitrogen or helium, could produce thrust without obvious optical manifestations. Dr. David Jewett proposed a test. If undetected forces are operating, they should produce characteristic signatures in how position errors evolve over time. Systematic forces create accelerating position discrepancies, while random measurement errors create scattered, uncorrelated deviations. The residuals from our orbital fits should tell us which pattern we're seeing. Analysis of the residuals, the differences between predicted and observed positions revealed unsettling structure. Rather than random scatter around zero, the residuals showed trending behavior, consistent, small offsets that accumulated over time before suddenly jumping to different values. It looked almost like the object was following a smooth trajectory, then abruptly changing course, then following another smooth trajectory. This is step function behavior, Jewett observed. It's what you'd expect if the object was executing discrete maneuvers rather than experiencing continuous acceleration. That's extremely unusual for a natural body. The maneuver interpretation immediately triggered renewed speculation about artificial control. Objects under intelligent guidance execute discrete course corrections, firing thrusters to change velocity, then coasting until the next burn. Natural comets experiencing outgassing produce more continuous, gradually varying accelerations tied to rotation and solar heating cycles. Dr. Paul Weig, examining the timing of apparent maneuvers, found them uncorrelated with any obvious natural cycles. If these trajectory changes are real and not artifacts of insufficient data, they don't align with the nucleus rotation period, solar distance changes, or any other natural periodicity I can identify. The timing appears essentially random from a dynamical perspective. Random timing, of course, changes was difficult to reconcile with any natural mechanism. Outgassing responds to solar heating, which follows predictable diurnal and seasonal patterns. Structural failures occur when stress exceeds strength, which should correlate with thermal or rotational forcing. What natural process would produce unpredictable, discrete velocity changes? Dr. Bonnie Burotti proposed an analogy. Consider a nucleus that's fractured into multiple loosely bound pieces, like a rubble pile held together by weak self-gravity. As different pieces heat, cool, and outgas, the internal stresses redistribute. Eventually, the configuration becomes unstable and the pieces shift relative to each other, suddenly changing the mass distribution and altering how outgassing produces net thrust. Each reconfiguration event would produce what looks like a discrete maneuver. This rubble pile instability model was physically plausible and could potentially explain stepwise trajectory changes, but it predicted that the nucleus should be visibly evolving, changing shape, brightness, distribution, or coma morphology as pieces rearranged. High-resolution imaging from the Mars encounter period showed some variation in coma structure, but nothing as dramatic as wholesale nucleus reconfiguration. As January ended and 3.1 ATLA as faded past magnitude 14, the trajectory mystery remained unresolved. The object had gained more velocity than observations could account for, through mechanisms that remained unclear. Future observations would be limited to astrometry measuring position but not brightness variations, spectra, or other diagnostics that might illuminate the acceleration mechanism. Dr. Alan Harris, from the Space Science Institute, reflecting on decades of asteroid and comet dynamics work, offered perspective. In my career, I've analyzed thousands of small body most follow gravitational predictions perfectly. A few show modest non-gravitational effects that fit standard outgassing models once you tune the parameters. 3.1 ATLAS is the first object I've encountered where the motion fundamentally doesn't make sense, where accumulating more data and refining models makes the discrepancies worse rather than better. That's deeply unsettling for someone who's spent a career believing we understand orbital mechanics. The velocity discrepancy joined the growing list of 31 ATLAS anomalies that individually might be dismissed as measurement uncertainty or modeling inadequacy, but collectively painted a picture of an object that systematically defied conventional understanding. It was accelerating. It was decelerating faster than it should. It was experiencing forces that weren't being detected, and it was executing what looked disturbingly like deliberate course changes. The word terrified never appeared in official NASA communications. The approved vocabulary included concerned, puzzled, and at most surprised. But in private conversations, in encrypted emails between colleagues, in late-night video calls when exhaustion lowered professional guards, a different tone emerged. Dr. Lindley Johnson, NASA's planetary defense officer, expressed it most directly during a closed-door briefing to the Office of Science and Technology Policy on January 25th. If 3 IATLAS represents natural processes we don't understand, that's a significant gap in our knowledge, with implications for how we assess threats from interstellar objects. If it represents something else, and I want to be very clear that we have no evidence supporting non-natural explanations, then we're confronting a category of phenomenon we're not prepared to address. The briefing, later leaked to Science magazine, laid out the accumulating evidence systematically: trajectory anomalies, sustained acceleration and deceleration, exceeding what outgassing models could explain, discrete velocity changes appearing like deliberate maneuvers, position errors accumulating to hundreds of thousands of kilometers despite intensive tracking, energy budget problems, highly ionized emission requiring extreme temperatures, metal vaporization rates demanding power inputs far exceeding available solar heating, rapid eruptions cycling faster than thermal processes should allow, magnetic effects, correlation with Mars's magnetotail suggesting electromagnetic interactions, induced magnetosphere apparently stronger than typical comets by an order of magnitude, chemical anomalies, sequential activation of different elements as if layers were being excavated, sodium-rich composition unlike typical solar system comets, isotopic ratios when measurable at the edge of solar system ranges, structural behavior, brightness variations on 8-minute timescales requiring non-rotational explanations, debris trail aligned with trajectory suggesting continuous low-velocity mass loss, light patterns showing structure rather than randomness. Each category contained observations that, while puzzling, could potentially be explained through exotic but natural mechanisms. The accumulation of anomalies across multiple independent categories was what concerned researchers. The probability of this many unlikely things happening simultaneously in one object, purely by chance, is extraordinarily small, Johnson's briefing noted. Either 3I, Atlas, represents an extreme statistical outlier, the 1 in a billion comet that happens to violate expectations across every observable parameter. Our assumption space needs expansion. Dr. Sarah Seeger, MIT astrophysicist and exoplanet researcher, was invited to provide external perspective. Her assessment was characteristically direct. The astronomy community has spent decades searching for technosignatures, evidence of technology in astronomical observations. We've developed sophisticated frameworks for distinguishing natural from artificial phenomena in contexts like SETI. Those same frameworks, applied to 3i Atlas, suggest, at minimum, that artificial origin deserves serious consideration alongside natural hypotheses. Seeger emphasized this wasn't a claim of alien technology, but rather an argument about proper scientific methodology. When observations don't fit natural models, even after extensive efforts to make them fit, expanding the hypothesis space to include alternatives is sound practice, not speculation. The key is maintaining proportionate confidence. Artificial origin as a testable hypothesis rather than accepted. Conclusion: the challenge was that most technosignature frameworks assumed detection of deliberate signals, radio transmissions, optical beacons, or megastructures designed to be noticed. 3.1 ATLAS, if it represented technology, would be doing the opposite, transiting through our solar system on a trajectory that didn't obviously target anything, exhibiting behavior that drew attention through anomalies rather than clear signals. Dr. Jason Wright from Penn State, who directed the Extraterrestrial Intelligence Center, outlined what coherent artificial hypothesis might look like if we're seriously considering this. And I want to emphasize that if we'd be looking at something like an interstellar probe that's malfunctioning or damaged, the erratic behavior, unexplained energy outputs, and trajectory irregularities could represent a technological object operating outside design parameters. This would explain why it looks anomalous, rather than clearly artificial. The malfunctioning probe hypothesis had certain appeal because it explained anomalies through a single mechanism rather than requiring multiple unlikely natural processes. But it immediately raised the question: if this was technology, where was it from and why was it here? Dr. Avi Loeb, predictably, had already published preliminary analysis exploring this question. If 3i Atlas originated as a technological object, its current trajectory suggests launch from a stellar system within roughly 1,000 light-years, assuming travel time of a few million years at typical interstellar velocities. The originating civilization would need to have achieved spacefaring capability during a period when complex life was already well established. On Earth, the timing wasn't impossible. Life could have evolved earlier elsewhere in the galaxy, but it added another layer of speculation to an already highly speculative scenario. More problematic was explaining why such a probe would visit our solar system. If the purpose was observation, why not enter a stable orbit rather than passing through on a hyperbolic trajectory? If the purpose was resource gathering or terraforming preparation, why show no evidence of such activity? Dr. Jill Tarter, former director of SETI Institute, offered cautionary perspective. Throughout SETI history, we've encountered numerous signals and observations that initially seemed to defy natural explanation. The WOW signal in 1977, fast radio bursts when first discovered, tabby stars, dimming patterns. In every case, continued observation and analysis either revealed natural explanations or showed the phenomena couldn't be definitively classified. Jumping to technological conclusions prematurely has consistently led us astray. The scientific community's discomfort with the artificial hypothesis stemmed partly from lack of positive evidence. No signals detected, no geometric structures observed, no obvious purposeful behavior, and partly from awareness of how easily humans project agency onto ambiguous phenomena. Dr. Caleb Scharf from Columbia University articulated this concern. Humans are pattern recognition machines. We see faces in clouds, agency in random events, purpose in coincidence. The history of science is partly a history of learning to distinguish real patterns from paradox. When we encounter something that doesn't fit our models, our instinct is often to attribute it to intelligence because intelligence is familiar. We understand how purposeful agents behave. But the universe is under no obligation to conform to our intuitions about what natural phenomena should look like. Yet that argument cut both ways. If natural phenomena could produce any behavior, including what looked like deliberate maneuvers and energy outputs requiring technology, then the distinction between natural and artificial became meaningless. At some point, accumulating anomalies demanded expanding hypothesis space beyond conventional natural mechanisms. The debate reached broad public awareness through a February 1st article in The Atlantic titled "What Scientists Are Really Thinking About 3I, ATLAS." The piece, based on interviews with dozens of astronomers, revealed the uncomfortable tension between public statements emphasizing natural explanations and private admissions of genuine uncertainty. One anonymous senior astronomer quoted in the article, off the record, "I'd say there's about 20% chance this is something we'd classify as non-natural if we had all the facts. On the record, I say we need more data before drawing conclusions." Both statements are true, but they convey very different impressions about the state of our understanding. The public response was predictably polarized. Social media exploded with speculation ranging from sober discussion of observation techniques to elaborate theories involving alien artifacts, ancient astronaut scenarios, and government cover-ups. The hashtag #3IATLAS is alien trended alongside hashtag natural, not alien, creating a discourse environment where careful, scientific uncertainty was drowned out by confident assertions from both extremes. NASA found itself in the uncomfortable position of trying to communicate nuanced uncertainty to a public that wanted definitive answers. Dr. Thomas Zurbuchen addressed this in a February 3rd press conference. Science thrives on uncertainty. What looks like indecision to the public is actually the engine of discovery, holding multiple hypotheses simultaneously while gathering evidence to distinguish between them. The moment we claim certainty about 3I ATLAS, we stop doing good science. As February progressed and the object faded beyond even the largest telescope's reach, the window for gathering additional evidence closed. What remained were the data archives, the competing interpretations, and the unsettling recognition that humanity had observed something that defied comprehensive explanation, using available frameworks, whether that represented a profound gap in natural understanding or evidence of something fundamentally different remained, frustratingly, an open question. On February 15th, 2026, the Subaru telescope in Hawaii captured what would stand as the final confirmed observation of 3I ATLAS. The image required for hours of exposure, time, and sophisticated noise reduction algorithms to distinguish the magnitude 16.2 object from background galaxies. Dr. Tsuyoshi Terai, who obtained the observation, summarized the moment with understated finality. "We have position, confirmation that the object still exists and continues outward. Beyond that, we can say very little." The final trajectory solution, published by JPL on February 20th, projected 3 IATLAS's future path with steadily expanding uncertainty. The object would cross Jupiter's orbital distance in late 2027, reach Saturn's orbit by 2032, pass Uranus by 2045. Beyond that, predictions became essentially meaningless. The accumulated effects of unmeasured forces created uncertainty cones spanning billions of kilometers. We've lost it. Dr. Davide Fornocchia admitted in the final trajectory update, not in the sense that we don't know roughly where it is, but in the sense that we can't predict its future motion with useful accuracy. If it continues accelerating, or maneuvering as observed during the inner solar system passage, its actual position could differ from predictions by astronomical units within a decade. The loss of predictive capability carried practical implications for planetary defense. If interstellar visitors could execute unpredictable trajectory changes, assessing whether they posed impact threats became fundamentally more difficult. An object appearing to pass safely distant might maneuver onto collision course. Conversely, resources spent tracking an apparently threatening object might be wasted if it maneuvered away. Dr. Linley Johnson's February 25th report to the Planetary Defense Coordination Office was blunt. 3. IATLAS demonstrates that our threat assessment protocols, designed for objects following predictable gravitational trajectories, may be inadequate for a subset of interstellar visitors. We recommend development of enhanced monitoring strategies and consideration of scenarios where trajectory, prediction, uncertainty remains high even with extensive observation. The recommendations included deploying space infrared telescopes capable of detecting objects approaching from the sun's direction, the blind spot that had allowed 3.1 ATLAS's trajectory deviations to accumulate unnoticed. They also called for rapid response spectroscopic capabilities that could characterize object composition and activity within days of discovery, potentially revealing unusual properties before they created trajectory surprises. Budgetary realities made immediate implementation unlikely, but the 3I Atlas experience had demonstrated gaps that could no longer be ignored. The next interstellar visitor and statistical models suggested perhaps 1 or 2 per decade would be discovered, would arrive into a more aware, if not better prepared, observation infrastructure. The scientific legacy of 3I Atlas was still being tallied as researchers continued. Analyzing the accumulated data, Dr. Matthew Knight coordinated an international working group tasked with producing a comprehensive review of the observations and their implications. The preliminary outline, circulated in early March, included chapters on trajectory dynamics and non-gravitational forces, documenting the acceleration, deceleration, and apparent discrete maneuvers with full uncertainty analysis, spectroscopic observations, cataloging the detected chemical species, including highly ionized atoms and their implications for energy sources, photometric behavior, analyzing the multi-timescale brightness variations and their potential physical mechanisms, Mars encounter observations, synthesizing spacecraft data including magnetic field correlations and atmospheric effects, composition and structure, integrating chemical, isotopic, and structural inferences into coherent formation scenarios, comparative analysis placing 3I Atlas in context with previous interstellar visitors and solar system comets. The review would be comprehensive, running to hundreds of pages with extensive appendices of raw data and analysis code. But Knight acknowledged it would also be incomplete. We're documenting what we observed and presenting hypotheses consistent with subsets of the data. What we can't do is provide a unified explanation that accounts for everything simultaneously, while remaining within the bounds of established physics. That's the honest conclusion. We observed something. We don't fully understand this. Admission of incomplete understanding was simultaneously humbling and energizing for the research community. Dr. Sarah Seeger articulated the perspective. 3I ATLAS represents precisely the kind of observation that drives scientific progress, something that doesn't fit current models and forces us to expand our frameworks. Whether the explanation ultimately involves exotic natural processes or something more radical, the process of figuring it out advances our understanding. Public interest in 3I ATLAS remained high even as the object itself faded from telescopes. Documentary producers, science journalists, and educational content creators continued producing material about the mysterious visitor. The tone varied from sober scientific analysis to breathless speculation, but the common thread was genuine fascination with an authentic cosmic mystery. Dr. Pamela Gay's YouTube series on 3I ATLAS, which had been documenting observations in real time since discovery, concluded with a February reflection. We don't know what 3I Atlas was. We may never know for certain, but we've learned something valuable. The universe still contains mysteries, and our models, however sophisticated, remain incomplete. That's not a failure of science. That's why science remains exciting. The question of whether 3I Atlas would influence future space mission priorities generated extensive discussion. Several researchers proposed dedicated interstellar object interceptor mission spacecraft pre-positioned in the outer solar system, ready to deploy toward newly discovered visitors for close-range investigation. Dr. Jean-Pierre Lebreton, former ESA Huygens project scientist, outlined a conceptual mission. Imagine a spacecraft with ion propulsion, capable of matching velocity with interstellar objects during their brief passage through the inner solar system. It would carry imaging systems, spectrometers, magnetometers, and dust analyzers, the full suite needed to characterize composition, structure, and behavior at close range. Such a mission would cost billions, but would definitively answer questions that remote observation leaves ambiguous. The technical challenges were formidable. Interstellar objects moved at velocities requiring enormous delta-v budgets to rendezvous with. Their discovery often came with limited warning weeks, or months rather, than the years typically needed to plan and execute space missions. And their unpredictable behavior, as 3I demonstrated, meant that mission plans might become obsolete if the target maneuvered unexpectedly. Nevertheless, mission concepts were being refined. ESA's Comet Interceptor, already under development for launch in 2029, would demonstrate relevant technologies, while designed to target long-period comets from the Oort cloud. The mission architecture could potentially be adapted for interstellar visitors if discovery timing aligned favorably, as March 2026 arrived and 3I ATLAS's passage into history became increasingly certain. Attention turned toward the future. What would the next interstellar visitor reveal? Would it show similar anomalies, suggesting 3I Atlas represented a genuine class of objects with unusual properties? Or would it behave conventionally, implying 3I Atlas was a singular outlier? Dr. Alan Harris offered perspective based on decades of small body research. sample size matters enormously in astronomy. With 3 confirmed interstellar objects, Oumuamua, Borisov, and 3I, Atlas, we have barely begun to sample the population. Each one has surprised us in different ways. Only after observing dozens or hundreds will we understand what's typical versus exceptional among visitors from other stellar systems. The waiting period for the next discovery was uncertain. Detection probabilities depended on multiple factors: object size, activity level, trajectory, geometry, and survey telescope capabilities. Optimistic estimates suggested the Vera Rubin Observatory, beginning science operations in late 2025, might detect several interstellar visitors per year once fully operational. More conservative projections suggested 1 every year or 2. Whatever the discovery rate, 3.1 Atlas had established that these objects deserved intensive follow-up. NASA, ESA, and other space agencies had implemented new protocols for coordinating rapid response observations when interstellar visitors were detected. The astronomy community had learned from the trajectory prediction failures and observation gaps that characterize the 3.1 ATLAS experience. The final public statement from NASA's Planetary Science Division, issued March 15, captured both the accomplishments and uncertainties. 3. IATLAS provided unprecedented opportunity to study an interstellar visitor during its passage through the inner solar system. The observations revealed an object with properties and behavior that challenge current understanding. While many questions remain unanswered, the data collected will inform research for years to come and prepare us for more effective study of future visitors from other stellar systems. As 3I, Atlas continued its outward journey, invisible now even to the most powerful telescopes, becoming a mathematical abstraction rather than observable object, left behind something valuable: the knowledge that the universe retained capacity to surprise even sophisticated 21st century astronomy. The visitors traveling between stars carried secrets that Earth-based observation couldn't fully reveal. Understanding them would require patience, improved technology, and willingness to confront the possibility that some cosmic phenomena operated according to principles we hadn't yet discovered. The mystery of 3I Atlas remained unsolved, but the search for answers had just begun.